In this video, we're going to start to take a look at equilibria that arise in chemical processes. Now, an equilibrium is something that can occur whenever we have a reversible process. When it comes to chemical reactions, these can be considered to have a forward and a backward reaction. So the forward reaction would be taking those reactants, mixing them to form products, what we want to get out of that reaction. The reverse process, or the backward reaction, is those products reacting with one another to turn around and reform our original reactants. For some reactions, the rate of that reverse reaction is so small that all reactants are completely or essentially converted to products. And when that's the case, then our reaction is said to reach completion. And we represent those scenarios using single arrows. So this would have been a lot of the chemical reactions you would have seen in your first semester course. So here we have an example of hydrogen reacting with oxygen to produce water. So even though water can technically break apart and reform hydrogen and oxygen, that process is so slow that it essentially happens very minimally. Now, an equilibrium reaction is going to be what we actually come across more commonly. Many reactions do not actually reach completion. This occurs whenever the rate of our reverse reaction is fast enough to result in significant amounts of reactants being reformed. Now, that's going to have an impact on amounts of materials that we use and amounts of products that we get formed. And so we need to distinguish between when our reactions go to completion, so all of the reactants form products, versus a scenario where some of those products reform our reactants. And we do that using a double arrow. So we have this example here of N2O4 producing 2NO2. And notice we have the double arrow. Now each direction, so that forward and that reverse, each direction initially has its own rate. But remember when we talked about rates previously, those rates change over time. So as the concentrations of our reactants go down, that rate decreases. So over time, the rate of our forward reaction is going to decrease as those reactants get used up. But at that same time, we've got that reverse reaction going on. And the rate of that reverse reaction is going to actually increase over time because the more products we have available, the more collisions we can have, and they can turn around and reform reactants. So over time, the forward rate goes down, the reverse rate goes up. These are happening at the same time. Eventually, they're going to become equal. And that point in time, when they become equal, that is when we get what we call a dynamic equilibrium. So a dynamic equilibrium occurs when the rate of the forward reaction or process equals the rate of the reverse reaction or process. So in the case of a chemical reaction, products are breaking up and forming reactants just as fast as reactants are forming products. We get a constant interchange of reactants and products and no change in our concentration. As a result, the concentration becomes constant. And because the concentration becomes constant, the reaction appears to stop even though it really hasn't. Reactants are still forming products, products are still forming reactants. They just happen at the same rate, so there appears to be no net change. So again, we need to distinguish when we have a process that's going to either go to completion versus going to equilibrium. And so we said we're going to distinguish between those based on the arrow that we use. And so if we have a reaction that's going to completion, we're going to use the single arrow. Equilibrium, we're going to use the double arrows. So we're asked, does a reaction that reaches equilibrium ever really stop? And the answer is no. It appears to stop because the concentrations become constant, but the reaction is still moving. It's just happening at equal rates. Now, oftentimes there is confusion about the term equilibrium. It does imply things are equal, but what it's indicating is equal are the rates for our reaction. So when we're asked our concentrations, our reactant concentrations and product concentrations equal, that is not what we mean by equilibrium. Equilibrium just means the rates are equal. Concentrations may or may not be equal, so they are not necessarily equal at equilibrium. Most often, they're not. So then we have this scenario. We've got the reaction of, and it's just a generic reaction, of A reacting with B, producing products C and D. And we're asked, are the concentrations of A, B, C, and D changing if we have 100 moles per second of A and B being used? They're being converted into C and D by our forward reaction. And at the same time, 100 molecules per second of C and D are being converted into A and B. So for every 100 molecules of product we form, we turn around and use those 100 molecules and we reform the reactants, which means they're not changing. So we use 100 molecules of reactants, we form 100 molecules of product. We then use 100 molecules of product to reform 100 molecules of reactants. So the 100 we use, we get right back because they're happening at the same rate. So again, no, their concentrations are not changing. C and D reform reactants just as fast as they are getting formed. Now, when it comes to our equilibrium, and we're getting a foundation of equilibrium here, we're going to see equilibrium applied to other concepts later on. But when we talk about an equilibrium, it can be described as being either homogeneous or heterogeneous. And that's going to be in reference to our phases. So are the phases all the same or are they different? Say a homogeneous equilibrium is where all of the reactants and products are in the same phase. So here with the reaction of hydrogen with nitrogen to produce ammonia. My hydrogen and nitrogen are gases. My product is a gas. They're all the same phase, so it's a homogeneous equilibrium. A heterogeneous equilibrium is one in which at least one reactant or product has a different phase from the others. So if one thing is different, it's going to be heterogeneous. Here we have a mixture. I've got solid magnesium carbonate, I've got solid magnesium oxide, and I have gas for my carbon dioxide. I have different phases. And since those phases are different, that's going to be described as being a heterogeneous equilibrium. So we want to be able to look at different reactions and classify them or describe them as being either homogeneous or heterogeneous. So with A here, we've got gaseous hydrogen reacting with gaseous carbon dioxide, producing gaseous water and gaseous carbon monoxide. All of my phases are the same, so this is a homogeneous equilibrium. And then next, we've got this solid ammonium chloride decomposing into gaseous ammonia and gaseous HCl. My phases are different, so this is going to be a heterogeneous equilibrium. And then finally, we've got solid sodium chloride producing sodium cations and chloride anions. I've got solid and then aqueous. They're not all the same phases, so again, this is a heterogeneous equilibrium. So an equilibrium can occur when we have a reversible process. So in the case again of our reaction rates, if we have a scenario where a reverse rate has a significant rate that we can produce significant amounts of reactants, we're going to have this equilibrium occurring. And so we're going to get to this point where we kind of have this standstill. The concentrations no longer change, they become constant, and my reaction appears to have gone as far as it can go. The consequence of that is that when our reaction stops, it's not really stopping, but when it essentially stops, we have a mixture. Unlike a reaction that goes to completion, that reaction that goes to completion, all of the reactants become products. Here, not all of that occurs. So we get a mixture of reactant and product at equilibrium. So in our next video, we're going to take a look at describing that equilibrium mixture.